Good morning, good afternoon, and thank you for attending this fourth episode of the Probability of Default. As you may know, my name is Rafael Castillo. I'm using the nom de plume Raf Castle, which was the basis for the book Probability of Default, which is the main inspiration of these episodes. Let me start by explaining why we and I decided to make the purpose this year to drill down and understand the concept of probability of default. And the main driver for that has been a little bit of frustration and disappointment. With all the people and companies with whom we interact, and my profession is in the consulting business for the financial industry worldwide. I found out that most of the people and most of the companies that show or should show any credit culture randomly, they don't really understand the concept in itself. And it makes me miss the old times when the bankers were based on the gut feelings. I remember the story of JP Morgan when he decided to buy from Andrew Carnegie US Steel, United States Steel, and that was based on a very good gut feeling that the banker developed. That gut feeling has been lost over generations. Probably that came at the beginning of the 20th century. And nowadays, what we find, especially when we start dealing with financial institutions or even companies that are in the business of selling on credit terms, when we ask them about their credit culture, we don't really receive a convincing answer. And that's the reason why I would like to ask all of you and encourage you to think whether or not you have in your organization or even in your own life, because when we talk about default, it's not only default in credit terms. Default, as we saw in one of our prior episodes, is the outcome of broken promises. So today we are going to see the progress that has been made by probability science, and in particular, the contribution of the law of large numbers. So here's a question that I wanted to ask, and I want you to reflect about that, is do you have your own credit culture? And that means something that emerged from your shared learnings. As an organization, you learn a lot of lessons, and normally if your organization is integrated by many people in the same business, in the same industry, sharing the learnings is one of the main foundations of any culture whatsoever. And that drives the beliefs. Once we see what works and what doesn't work, then we start believing in something. And finally, we create a hierarchy of things that work and don't work. And that eventually gets us into addressing or assessing a value to some of the conclusions that we are getting from our experience and from the lessons learned. So that's the question for you, because what we have seen in general is that most of these organizations are borrowing someone else's credit culture. And when we ask, doing, for example, due diligence on financial companies or talking to the bank's credit officers and the board of directors, how do you appraise your credit? And they say, oh, no problem. We bought the model from Moody's, or we have the Standard & Poor's or the KBR, which used to be Duff & Phelps, and Duff & Phelps was purchased by Kroll, or Fitch Ratings. But do you really understand how they work? Do you really understand, and does it have any correlation with the way as you approach credit risk? And at least from my personal perception, the answer is no. I mean, nobody knows exactly how the Moody's analytics model works. We are going to examine that model in future episodes because it's very critical. But just to give you an advance, we are going to talk today a little bit about one of the foundations of the Moody's problem, which is the Merton formula. We are going to talk about the Merton formula a little bit today because we will touch some base on that. But most of the people don't understand why do you use the Merton formula, and is it really conductive to really understand what is the probability of default that we are facing? So this is one of the key questions that I want you to reflect about. And the second question has to do with what is the importance of this episode and further episodes. In practical terms, you may be in the business of financing or you may be in any other business. If you are in the business of financing, certainly this travel, the trip we are currently taking together, the journey we are taking together, will help us understand where the foundations of probability of default come from. And that will avoid the shame of believing without understanding. So now we will understand what is the foundation of the probability science and how does that could apply to our analysis of probability of default. And today's episode is going to be very, very interesting because we are going to see a lot of progress in terms of the science of probability that will help a lot to give us some food for thought in terms of how to enrich our approach to probability of default. But it is not going to give us a panacea. And there have been a lot of mistakes that have been done following the thread of what we are going to see today, considering that this is the real basis, that is the gospel of probability of default. It isn't, but it's a great, great leap forward. Now, so we have in practical terms two situations. The first one, you are in the business of financing, and certainly you are bound to calculate probability of default as part of your obligation to estimate your expected losses. And even the impact that the probability of default has in unexpected losses, which also drives in terms of financial institutions, the amount of capital adequacy, the minimum capital you need to hold in order to keep your business in place. That, for example, is a very relevant issue today for Credit Suisse, which is, as you know, we are hearing the cracking of Credit Suisse while we speak today. Hopefully, we are not going to have a second Lehman Brothers, but this is something that is happening, and I hope that this shoe will not fall soon. So the point is, if you are not in the financial business, but if you are in the commercial business, in the business of selling goods or services, and we generally deliver the goods or deliver the services prior to receive payment. Generally, that happens. And when that happens, then we are subject to credit risk. There is an accounting standard, IFRS 9, that is in force since 2018, and in the US will become effective the similar accounting standard January 1st, 2023. And both of them are binding business persons to apply the current expected credit loss accounting, which means we need to create and have a methodology and have policies and processes in order to calculate the probability of default. So this is a big deal. It's something that certainly is going to help a lot in terms of complying with this. But not only that, it's not only an issue of compliance, it's an issue of really understand and improve our quality in the business. So here's the path that we have been following, and is the path that in the book itself I have been following in order to understand and to learn from scratch the concept of probability of default. So we started talking about the concept itself of probability of default, going from the layman perspective and talking more about practical experiences than theory. Then we focus on the concept of default, and we found out that certainly default is essentially the outcome of broken promises. So that's the reason why I say that when you are able to estimate probability of default, is not only for credit terms, it's also for any kind of human relationship, because we are always bound to promises. Your spouse is promising you something. You promise something to your spouse as well. And the point is that how can we really evaluate the probability that this promise is not going to be broken? So that was part of the process. All the prior episodes are available to be watching in YouTube. So so you can certainly catch up if you want in going into the whole thread of things. We are currently in the stage of understanding the science of probability, the probability theory, and that will give us enough knowledge to define what is or what should be the risk appetite framework that all of us should have in our real life and in business. And then we are going to move forward into specific areas such as understanding the impact of the concept of character, the evaluation of character as part of the probability of default, getting more in detail and evaluating the different models that have been in the market for estimating probability of default. And finally, getting into the concept of what we can build as a methodology in order to calculate probability of default. So getting into our next point is just a suggestion. If you are in a hurry and want to get faster to the end of the journey, well, you can go to Amazon and buy the book and read the book. I hope that you will find this reading very entertaining. I believe I have been talking with some people that are not very much in the scientific side of the business, and they have the feedback I receive is that the book is readable and it's understandable. And that was my purpose, because I don't want to get you, as I didn't want to get myself, trapped into a lot of jargon and concept that we cannot understand. I want to be able to understand everything in the layman language, and that's something that is extremely important. So now, when we talk about probability of default, the question that we ask ourselves is, how do I know that the person who owes me money, if we are complaining just to money, is going to pay me back? Is the typical question that we ask every time we do business. Every time we wake up and we are expecting that our products and services are sold, or that the credit we are granting, the loans we are granting, or the leases we are granting are going to be paid back. And that makes us land into two secondary questions. One is how can I estimate that that person is willing to pay? And that will take us to the concept of evaluating character. And the second one is, how do I estimate that that person has the capability to pay? And that is a problem of distance. So probability of default is essentially the calculation of the distance between the situation today of these two drivers, character and capacity, and the ability to someone to fulfill its promises. Now, let me just recall a little bit what we have learned in the former episodes. The first concept clearly is that default is a human behavior where character plays a big role. And of course, it has to do a lot with personal freedom. Second, probability emerged as a scientific concept when men understood that the future is not something imposed by the gods, but that we can really anticipate the future, albeit not necessarily we can predict that specifically. The best example is what happened a week ago when the Hurricane Ian hit the coast of Fort Myers. It was not expected by the population of Fort Myers. Everyone was expecting that the hurricane was going to hit in Tampa, further north, and it didn't. So you can imagine that, yes, we know that the hurricane came. We have all these aircraft flying over the eye of the hurricane and predicting its course, but it's not totally accurate. So the third concept that we learn is that probability science is rooted in mathematics, and the starting point came from the seed planted by Fibonacci, who actually brought to us the developments of mathematics coming from the Middle East. And also, was our last episode, curious gamblers, such as Fra Luca Pacioli, Girolamo Cardano, the Chevalier de Marais, Blaise Pascal, and Pierre de Fermat. They produce what we call the Big Bang in probability science, because that at that moment when we started to create a methodology that is supported by the application of mathematics. So today we are going to receive the visit of what we call the stochastics. Could be the title of a movie, The Untouchables. But when we talk about the stochastics, we talk about people that are dedicated to analyze random situations. And that is something that is very important to consider, which is we make decisions based upon very limited data. Let's talk about data for a minute. Data is essentially information translated into a form that is efficient for movement or processing. That's the academic definition of data. Data could be certainly the outcome of experiments. Data can be the observations or facts, as we are going to see. But what is interesting here is that we need to understand that, for example, when you look every morning to the Dow Jones Index, probably you are not aware that the Dow Jones Index is only indicative of the behavior of 30 stocks out of more than 500 stocks that are listed in the New York Stock Exchange and in the whole exchanges around the United States and the world. So only 30 companies are going to give us the sense of how the economy is moving. Only 30 companies. Same happened when we talk about political polls. In the last election in Brazil, one of the main outcomes of the election is that the polls were wrong. Well, usually polls take a sample of around 2,000 people, no more than that, to evaluate the willingness to vote of more than 100 million people. So this is a little bit what shows how things work in terms of starting by some little sample of data and becoming that the whole expected through. And probably the best example is when you get into a restaurant, a sip of wine will tell us if we can drink the whole bottle or not. I have a little bit of an embarrassing story about that, because one of the situations here is not only the sip of wine, you need to be an expert on that, and I'm not an expert. So I remember that I was presiding a dinner with some friends from the Middle East, from the Sultanate of Oman, and I was offered a bottle of red wine in Italy by the waiter. Well, I took the sip of wine and said, okay, it's okay, take it. My friends, they didn't touch the glass. And then the next day I realized, and I apologized to them because I said, sorry, I think I offended your religious beliefs. You're Muslim, you don't eat, you don't drink alcohol. And the reply really was amazing. They said, no, you are mistaken. They invited me to have a very good, nice glass of wine, Chateau Petrus. They said, the problem is that you know nothing about wine. And the sample you took was totally wrong. So that's the reason why we didn't touch the wine. So again, we are talking about, very small samples that take us to the inference of the reality. And that has certainly an important development. How did it work, and how this really got us to the developments of the science of probability? Well, let's start by the year 2025, Annus Domini, in Rome. Ulpian, which was a Roman jurist, a praetor, which is a judge, he compiled the first set of mortality tables, how many people died in Rome. And that compilation is still available. I think that is, you can look that in the British Museum. It's a very, very interesting point that goes when people started to count a concept which is the number of deaths. That concept was then resurrected in a way by a gentleman called John Graunt, who in 1662 published a statistic of births and deaths especially in the city of London and around England, from 1604 to 1661. Interestingly, 1604 was the year after the Queen Elizabeth I died, and it showed a very interesting pattern of mortality. And we are going to look a little bit on that in the next slide. But it was very interesting because that was the first time when this concept of mortality and measuring mortality came into mind. Then, interestingly, a gentleman that probably you have heard about, Edmund Halley. Edmund Halley is the same astronomer who predicted that a simple comet goes back to Earth every 76 years. Last time it came, it was in 1986. So probably we are not going to see the next trip in our lifetime, or at least not me. But he was a very interesting person, and he decided to drill down on a more complete database, if you want, of births and deaths records of the city of Breslau that was developed by a gentleman called Carl von Neumann. And Carl von Neumann actually, or Neumann, put more details into for example, what was the age of the people that had died, what was the reason why they died, and there were more details because John Grant he got the statistics of how many people was born in that year, how many people died in that year, but he didn't record the ages of the people who died. The statistics that Halley measured helped for that. And what was the practical application? At that time, governments started by the Netherlands were selling annuities. I think that the Prime Minister of the United Kingdom should be delighted to learn that this is a good tool for raising funding in public financing. So basically what they did is that they offer rich people, rich merchants, that if they pay the government, if they lend to the government certain amount, the government will pay back annuities during their lifetime. So obviously the game of the government was to try to minimize the amount of payments, and that depended basically of how long will that person will survive. And these tables from Edmund Halley helped very, very much to make this kind of calculation. So that really create a very strong basis for the public finances of the governments. But also from the other side, it also stimulated the extension of the life insurance business, which started to flourish in a very interesting way after a Greek scholar started brewing coffee, and coffee became very popular in London. So John Lloyd's decided to open his coffee shop, and the coffee shop became the place where seamen and other people started to gather and started to bet and started to calculate probability of default, and started the insurance business itself. So Lloyd's is today probably the largest organization in terms of insurance worldwide. It keeps being the largest reinsurer worldwide. And that started in that coffee shop. It started a little bit fed by the data that people like Grant and Halley provided to them. So this is an interesting illustration. I took a comparison between the survival data that was released by Grant in groups of ages, and I compared that with the census of 2021. Didn't compare with the census of 2022, which actually is a little bit not as good because we have COVID and the mortality was higher in 2022 when it was measured in 2022. But 2021 gave us a very good idea. You can see, for example, that the survival rate when a person reached 6 years old was 64, while in 2021 was 99.3. So a lot of progress that technology has brought to us. If we jump into my age group, 66, so you'll see that only 3 people were alive at the times of Grant. Now we have 82 people alive. And that creates an interesting calculation. From one side, the odds of people to die within the next 10 years. Let's say we apply that for the business of annuities, and we make our calculation that we are going to require only to pay over 10 years the annuity that we are receiving today. So that's what will help us. All these percentages, all these odds will help us make the calculation of what is the amount that we need to pay on an annual basis to our providers of funds. And the other side goes into the odds of people to die before the age of retirement at 66 years old. And that also gives a good idea about how we need to allocate the contributions to Social Security. So you can see how important was the contribution made by this couple of gentlemen. It was certainly something that made a big revolution. And with that, we received a visit of very interesting persons, the Bernoulli family, Swiss mathematicians, Jacob, Nicolaus, and Daniel. Daniel is going to be analyzed. He's going to be our guest in our next episode because his contribution is absolutely outstanding to the development of a probability of default. But not only that, you may know that probably what makes possible that you travel today in airplanes is owed to Daniel Bernoulli. So that's part of the advantages that it brings. But let's talk about Jacob and Nicolaus, because these two gentlemen make a great contribution to the business of probabilities in general. And Jacob Bernoulli is well known because he was the one who formulated the law of large numbers. The law of large numbers is our central theme today. How did it come to existence, this law of large numbers, and what does it mean? Well, before getting into what Jacob created of the law of large numbers, we need to get back to another mathematician, Christian Huygens, who launched an observation. Remember that in all these developments in the probability of default theory, everything has been developing around games. And Christian Huygens made the observation that in a game of chance, the expected value is the product of the sum we expect to win times the probability of winning. To give you a little bit of flavor, when we are forecasting our business in our consulting company, we allocate expected revenues for each project and the odds or the probability that we are going to win that project. And that's what we call the handicap value. And adding all that is our expected value in the projections we made in our business. Sometimes we achieve that, sometimes we don't. But the interesting part of this methodology is that, as Huygens explained, if you toss a coin, the expected value should be the addition of A plus B, being A the number of heads and B the number of tails, divided by 2. So every time you toss a coin, if you get there, the expected value is going to be 50%. I mean, of course, if the coin is, as they call, a fair coin, which is something that certainly will provide a lot of advantages. So in a similar situation, if we go back to what we saw in our last episode, which was the Cardano table, in how you can anticipate the different odds and probabilities in a game of 2 dice. In a game of 2 dice, you have 11 possible combinations. 11 possible combinations that happen in different ways. For example, the number 2 is 1 plus 1. It only happens once. The number 3 happens twice. 1 and 2 and 2 and 1, taking the 2 dices. The number 4 happens 3 times. 1 plus 3, 3 plus 1, and 2 plus 2. So when you take all these different combinations, there are 11 combinations, and the outcomes are 77. getting on the methodology that I explained to you that we use, for example, to estimate our expected fees, then what you do is simply you multiply the outcome times the probability of that outcome to happen. And that gives you this, in the first case, 0.06. And if you add up all that, the result is going to be the same one that is dividing 77 by 11. That's number 7. And the interesting part is that that is the conclusion. In the game of 2 dice, the expected value is 7. That's the reason why in the craps game, the number 7 is a big deal. Why this is important? Because when you have an expected value, what Bernoulli observed is that if you start gathering data, any kind of data, this data, as soon as you perform more tests, more proofs, you are going to get average results that in large numbers are going to be close to this expected value. And this expected value is going to be also considered part of what is called the average value, the mean value. Now, Nicholas, after Jacob died without publishing his book that was called Ars Conjecturandi, which is, Ars Conjectandi, which is the art of conjecture. And basically what he meant is how we can really, based on a sample, get into a large conclusion applying the law of large numbers. So Nicholas said, well, what my uncle said is something that could be interesting, but I need to reinforce that. Then he contacted a very well-known mathematician called Abraham de Moivre. And Mr. de Moivre, initially he refused to work with Nicholas, but eventually he accepted. And he brought to us another concept which is even more interesting. And today, this is the key concept that the Basel Committee is demanding the banks to do, which is expected loss. Don't think about expected gain only. Take into consideration that whatever you don't win, you lose. So why don't you consider that you are going to have expected wins and expected losses? So that way, you are going to see that the data is going to get into one side whenever you win and the other side whenever you lose. And putting all this data, the distribution of outcomes tend to form a curve with a form of a bell, what we call the bell curve. So, of course, his contribution goes a little bit further because he creates a mathematical formula that help us to calculate all these numbers. And he also uses the Fibonacci sequence and the golden ratio in order to support his formula. So basically, this is the way as we can see the Moivre contribution. But the most important part of the contribution is that he observed that there is going to be a normal distribution when you got all this data, but there are some distances to the mean. And these distances can be calculated with the help of Pythagoras, because it's a Pythagoras triangle. If you go into a Cartesian plane and you can really create a triangle there. So by calculating the square root of the hypotenuse that is formed in that triangle, you can calculate what we call today the standard deviation. That's the concept that he brought into the game. This standard deviation has been represented by the lowercase of the Greek letter sigma. And the term is the degree of dispersion of the observations of data with respect to the means. Interestingly, this concept of sigma was very much applied into the best management of companies, I would say from the 90s to the year 2000. Jack Welch became famous for his application of Six Sigma in General Electric. Honeywell also used that very much, but where did that Six Sigma come from? Well, a gentleman, an engineer called Bill Smith, who worked for Motorola in 1986, he started playing with the same concept of the standard deviation, and he applied that to manufacturing lines, to manufacturing errors. And his aim was, if we aim to produce a minimum number of errors that will represent less than 6 sigma, 3 to the left, 3 to the right, less than 6 sigma defects, then we will be achieving excellence. And that was the creed of General Electric that at this time, at the times of Jack Welch, make the company very successful in all different areas. But of course, we need to get back from 1986 to the 18th century. Because in the 18th century, we have a new contribution of this new concept. So we have now this idea from Bernoulli that tell us you can have a small sample, you can really make whatever number of tests you want. Was in his case, he made an experiment with some pebbles in a bottle. Some were black, some other were white, and he made a combination of for 25,000 experiments until he arrived to the conclusion that the proportion between black and white was 3 to 2, and that was the expected value. That was the means, and every standard deviation based on the data will be calculated based upon the distance between this particular observation and the mean that was 3 divided by 2 or 1.5. Well, this is a priest, another priest. You can see that probably in the 17th, 18th centuries and even before, priests have the advantage that they live out of the alms paid by everyone to the parishes, so they didn't need to work but to pray and dedicate a business to research in intelligent projects. So they produce a lot of intelligence, and Thomas Bayes was one of these examples. He said, well, whatever you are measuring is okay, but don't take that for its face value. You need to consider that also whatever data comes need to be connected to the prior knowledge of the conditions related to such event. So something in the past, the health of someone that is going to die, the condition of the health is certainly a precedent that will indicate whether or not that person will have a larger probability of or higher probability to die or not. So his observation was illustrated by this example, which is we have 2 factories. One produces 60% or 60 pieces, the other produces 40 pieces, total 100%. And a defect happens in the outcome. If you don't put attention to what Bayes suggested, you will assume that the mistake was an error of production in factory A. But it happens that according to experience, factory A has only made 10 defects in the past, while factory B made 20 defects in the past, a total of 30. So if you really multiply the defects of A with the production, you will find that the probability of defects in factory A was 6, while the probability of defects in factory B was 8. That meant that instead of being, guilty factory A for being the most probably cause of the error of the defect, actually it happened to be factory B, because you should combine not only the production that they made, first part of the data, but also what you learn from the recent past, which is the behavior of this factory in producing defects. And that is certainly a big deal in terms of probability, because it shows us that as soon as we are gathering data, we need to create more and more data. Now, this makes us jump again to the 20th century. In the 20th century, a Russian genius, building on the Bayesian foundations, developed the concept of the Markov chains. And basically what he said is the same concept, but he goes a little bit further. Bayes is asking us to pay attention to the past. Markov is suggesting us to pay attention to the present in order to consider the future. So in a way, he said, whatever happened in the past, okay, is good, but we have different steps, different situations that are going to evolve. And probably the best example is the one that is illustrated here. A and B in this graph are cities that where some tourists arrive. Let's say that these are in an island, and we have city A and city B. In city A, according to the behavior of people in general, 30% of the people who arrive, they remain in the city, and 70% they go to city B. While being in city B, 20% of the people remain in city B, and 80% of the people return to city A. So what the Markov chain is helping us to calculate, and this is of course reinforced a lot by the use of computers, but what Markov is helping us to realize is, okay, so at the end of the next day, how many people are going to remain in city A and how many people are going to remain in city B? And the calculation is the following. Population of tourists remaining in city A should be 30% of 30% who have been remaining all the time. That makes 9%. Plus 70% of 80%, the people that went to city B but came back. 70% of the people living coming from city B, which were 80% of that is 56%. So at the end of the next day, we have 65 people in city A and 35 people in city B. Why this is relevant? I don't know if you have been following the Weather Channel, and when you follow the Weather Channel in your application, you'll find that this is moved by Watson, the IBM computer. And Watson is currently fed by the equations of Markov. So whenever you have any prediction of terms of meteorology, for sure, Markov is there, helping you making this kind of calculations. But then let's go back to at least the 19th century, because now we need to really test how do we know if our inference of data, because that's what we are taking. We are inferring from the sip of the wine that the bottle is good. We're inferring from the Dow Jones for the 30 companies that the economy is going up or down. How do we really reduce or minimize our margin of error? Because we are always taking small samples. And then there is a very interesting guy, an astronomer, that comes to our rescue. Johann Carl Friedrich Gauss. He is very well known for many reasons, but probably the most interesting part about his character is that he was born in a Wednesday of a certain day, in the Eastern week. His mother was illiterate. She didn't know it. She didn't get the date when he was born. But he was able to calculate the date when he was born based on the data he received from his mother. You were born on a Wednesday of an Easter week. So this shows a little bit how he was able to perform calculations. He dedicated his life to calculating the orbits of celestial bodies. And probably the most famous is his calculation of Ceres, which is one of the most accurate calculations. But at the end of the day, he ended up calculating the dimension and the length of the Earth. So the interesting part of that is that when he started analyzing everything, he said, well, in a distribution, we need to take into consideration that things are not in a straight line. I mean, one thing is walking from point A to B, and a different thing is flying from point A to B. The crow flight is different to the pedestrian flight or the man trip. And that helped him to really create a concept that was based on calculating the possible dispersion to the mean. And that is exactly what led to the so-called method of least square calculations. Because again, he took the same concept of the standard deviation, which basically takes a square method, and he calculated the least square separations, if you want, from the mean. That was a very big deal, because from there, the bell curve started to be called the Gauss curve. And the Gauss curve has been the basis of most modern statistics, because what it shows is that every data is going to gravitate around the same circle. The least square method was disputed by Gauss with Adrien-Marie Legendre, which was a French mathematician who actually published something in the same dates. So there was a dispute of who copied who. Probably no one copied no one there. But the other interesting anecdote about Gauss is that he lived in a city called Göttingen. And when Göttingen is close to Kassel, the place where the Grimm brothers lived in Germany, very close to Frankfurt, and some 2 hours by Autobahn out of Berlin. Very well known by his university. And it is told that at the time when Napoleon Bonaparte was invading what is today Germany, Prussia at that time, he decided not to get into Göttingen because that was the city where the most important mathematician of all times was born, and that was Gauss. The funny thing is that in retribution for that, he imposed a big fine to Gauss that eventually was paid by another mathematician, French mathematician, Laplace, because Laplace had the money, Gauss didn't. Now, after Laplace, then we jump into the Victorian era, and we find a very interesting guy, a very rich noble man called Sir Francis Galton. He was the cousin of Charles Darwin. His grandfather, or the same grandfather of Charles Darwin, wrote a book called Zoonimia, which is, I would say, the precedent of the Origin of the Species, the book by his grandson Darwin. But this guy, Galton, was a very interesting guy. He was obsessive with measuring. He was not very good at mathematics. He was good in measuring. And he decided to measure everything. He traveled a lot to Africa, to the colonies of the British Empire, was very well known in Africa, and he learned a lot about people. He wrote a book about the evolution of genetics, how people, second generation heights are related to first generation heights. And that interesting contribution led him to go into a concept that today is very important, which is the regression to the means. It's a little bit more the sophistication of what Gauss had developed, but he has enriched that with more observation, more data, more measures. And then essentially what he says is that in a data distribution, despite the observation of outliers are, data that goes out of this area that is compared to the curve, the distribution tend to get arranged around the averages. So that's where we are today. People, based on Bernoulli, based on Gauss, and based on Galton, we can reasonably believe that with the observations we have, again, the Dow Jones, we can infer that reality is going to follow the same patterns. And then that takes us to another interesting area, because that was, in a way, multiplied thanks to technology and thanks to very interesting observation. And that is the so-called Monte Carlo method, or Monte Carlo experiments. So Monte Carlo experiments help a little bit to aggregate all this data, make different combinations. The anecdote is that back in 1946, just 1 year after the atomic bomb of Hiroshima and Nagasaki were released, the Manhattan Project was working in the neutron bomb and the hydrogen bomb, but they were not able to perform the calculations to really find out what was the point where the neutrons will really create the boom, the explosion that was necessary for the bombs to work. And this gentleman, Stanislaw Ulam, you can imagine, he was a Polish immigrant into the United States. I mean, all the wealth and intelligence that has been created in the US have been driven by immigrants. And this gentleman, he got a flu, went home, and started playing solitaire. And then he started thinking, oh, how can I really calculate the probabilities that my solitaire is going to work, as opposed to having a solitaire that doesn't work? So he decided that the best way was creating different combinations, and the computer will help for this combination. I mean, it's something that we cannot do by hand. And doing that, they brought back the Markov chain as one of the feeding points, and started to perform in different combinations of different scenarios, different outputs. And that is exactly what the Monte Carlo simulation is all about, where you can really create different combinations and at the end of the day, observe what is going to happen in the distribution of data. And as you can see, again, we get a little bit the Gauss distribution here that is going to give us the average to the mean and will allow us to calculate the distances or the variances there. So that encouraged these three gentlemen, some years later, to develop what is called the Black-Scholes-Merton model. Very famous because this Black-Scholes-Merton model earned the Nobel Prize of Economy. The problem is that some years later, these guys decided to put their formula into play in real life, and they created a hedge fund called the Long-Term Capital Management Hedge Fund. Unfortunately, that hedge fund collapsed, and collapsed because, unfortunately, the formula was not true in all cases. I don't want to drill down too much in the formula because, again, we are talking amongst laymen. But there are some interesting observations in the formula which are interesting. Mu is a Greek letter that indicates the mean to a normal distribution. So what they do is, S here is the underlying, or the price of the underlying stock of an option. This, again, the Black-Scholes-Merton model was used to calculate the price, the fair price of options of different companies. And then you can make a lot of money because the formula should tend to be absolutely accurate. What did it show? It showed from one side the fluctuation in a way led to infinitum, if you want. And that's the reason why we have the natural logarithm. As you may remember, the natural logarithm is a logarithm with a base of the Euler number. And the Euler number is the number that was developed by no other than Jacob Bernoulli when he decided to calculate compound interest of 100% in different periods. I mean, if the reinvestment of the money will be made in different periods, let's say once a year, and then once every 2 months, every 12 months, every 24 months, and then going up to fractions of seconds of reinvestment. And then going into infinitum, the concept of the number will reach something like 2.78, and that is the Euler number. And that Euler number is the base of the logarithm. So the interesting part of this is that shows a little bit a tendency to try to calculate in all this scenario of an extended distribution, what will be the potential limit and how you can really grab that. And I think that was the mistake. We cannot really grab everything. This is what we need to understand. You can also see that the mean is also, in a way, being neutralized by the square of the sigma of the standard deviation, that is the variance, and also is in the denominator. So the formula, why this formula is important? We are going to see this formula again, because Merton, this formula is the formula he applied to calculate probability of default in his company, KMV, and KMV was purchased by Moody's. So nowadays, the methodology that Moody's follows in terms of calculating probability of default is based on this equation. Now, is that the right equation? We are going to have an episode where we are going to really test whether or not that equation makes sense or not. But the interesting part and the lesson learned here is that even though they developed and they took the Bernoulli, Halley, Bayes contribution to a very large progress based on the law of large numbers, that in this equation should have been, the climax of these findings. But unfortunately, it was not. Reality shows otherwise. And probably that's the most important that we need to learn. Not everything is absolute, but the contribution made by these gentlemen, and don't take me wrong when I'm criticizing them, was outstanding. I mean, this formula is very useful, but it's not the panacea. Now, who really told the emperor that he was naked? These two gentlemen. First, Benoit Mandelbrot. Benoit Mandelbrot was a very interesting individual who worked many years at the IBM Corporation. And he was an analyst of stock markets. And when he started analyzing the stock markets, he said, the contribution made by Bernoulli, by Gauss, by all these gentlemen was good, but you need to take into consideration that there are not necessarily normal distribution, which was the concept coming from Gauss, but we have also fat tail distributions. And probably the best example of fat tail distribution is what happened to us in 2020, March of 2020, when the COVID-19 pandemic came to place. The pandemic was not part of the normal distribution. But if you read the global risk report that was prepared by the World Economic Forum at the end of 2019, you would see that part of the data of risk that we should be concerned about was a pandemic. But we really chose to ignore that, and it hit us. So what Mandelbrot and Taleb is the author of the Black Swan, the book of the Black Swan, and he has a very interesting approach towards all this concept of probability. And they say, whatever you have learned about probability is fine, but you need to consider that not everything behaves along the lines of the regression to the means. There are fat tails distribution, and you must not ignore these black swans, these outliers that go out of the box. You need to consider that they exist and they can hit you. And so what Mandelbrot suggested, and there are many interesting books written by Benoit Mandelbrot, is think about a concept that he called fractals. And fractals is an amorphous substance. This is a fractal, what you can find here. This is a fractal, and the fractal is something that you can calculate, but you need to calculate each area in particular. Again, our friend Pythagoras will help us perform these kind of calculations. But you need to calculate, when you are analyzing data, the fractals and not necessarily the Gauss curve. You need to do both. I mean, you cannot ignore that. But you need to consider that the word, in the terms of Taleb, is the combination. Data distribution is a combination of mediocristan, everything that oscillates around the means, and extremistan, all these fat tail distribution, all these extremes that we choose to ignore. And again, these concepts need to be taken into account because these concepts eventually are going to hit us. So this is part of the good contribution, because while we review the big interesting concept of probability of default and the contribution made by the law of large numbers, we also need to take into account that the fat tails are something that certainly are going to impact us. And certainly, this applies when we are talking about probability of default. As we are going to see, probability of default is not something that you can deduct using a Gauss curve. You cannot, this is a little bit my fight with the FICO score. You cannot judge my credit score based on the behavior of my peers. My credit score depends on my own behavior, not the behavior of someone who has my age, my race, my sex, no, and my nationality if you want. No, we are different. And since we are different, you need to take that we are part of these fractals. You need to calculate probability of default based on these fractals and not necessarily the Gauss curve. Gauss curve could help for some general purposes. And this is in general what I would say that summarizes what we have learned today. The first one is that our friends, the stochastics, they are helping us to infer probabilities from data. And this is absolutely important. We need data. But also what we learn is, jumping from Gauntlet to Haley, is that the richer the data, the better the decisions we can make. So we need to enrich data. This is something absolutely important. And that's the reason why we need to figure out what are really representative data in order to make a decision, in order to estimate probability of default. This is very important because when Bernoulli was starting his work, Leibniz, our old friend who is one of the fathers of calculus, he wrote to him and he told him something very important. He said, yes, certainly nature has established patterns originating in the return of events. What he said is, history can repeat itself. But he made a big warning in Greek letters. He said, but only for the most part. So history repeats itself, but not necessarily always and not necessarily the same way. And that opened the door to the exploration of the significance of data distribution. So again, this is a great contribution that we have, the ability to use the law of large numbers to reach and to enrich our decisions. Certainly the contribution by Bernoulli, Gauss, Merton, and Galton, and some other of our visitors, take us to the comfortable path of forecasting the future as regression to the means. When you are doing financial projections, for example, surely your methodology is based on the regression to the means. And you use the correction by applying the standard deviation. And that's fine. But, this is not necessarily the whole truth. Only for the most part, as Leibniz used to say. Now, Mandelbrot and Taleb warn us that we need to do fact-checking. Look for the fat tail distribution. Don't ignore the fat tail distributions, as we ignore in 2019 the existence of a pandemic that hit us. So we need to really factor everything that is going on today with us. How are we going to get impacted by inflation coming in? How are we going to get impacted by the missile that was launched by North Korea last Sunday? How are we going to get impacted by the success or failure of the Ukrainians taking back what has been invaded by Putin and his eventual demise if he falls? So this is the kind of data that we need to really try to assess. How are we going to manage if Credit Suisse collapses? How are we going to manage if there is a conflict in Taiwan and we don't have access to chips? So all these are part of the facts that we need to consider, and that are part of the fat tail distributions to better understand what is representative data and how we can make decisions. So that means, in general, we need to avoid ignoring any single individual data that may have consequences to that. And of course, this will help us better understand the way as FICO scores are built, and also a technique that is very much used, is good, but not necessarily the full truth, which is the static pool analysis, where we take, a group of portfolios based on its vintage, and we analyze the behavior of these portfolios based on the date they were originated and other factors. Again, we need to enrich data. So these were the lessons that we got from our good friends, the Stochastics. So I want to invite you to our next episode. I will call you, probably will be in the next few months, because we are getting into very busy times in November and December. Probably in December, we may have the next one. And this is going to be very interesting, because we are going to talk about skills in the game. And when we talk about skills in the game, is not only the concept of character that I have referred many times, but also what the contribution made by Daniel Bernoulli to a very interesting tool for calculating probability of default. So I want to thank you for your participation today. As I mentioned, this event has been recorded, so anyone who wants to get back again can visit that in YouTube. Anyone who has any particular interest in terms of further developments here, well, you can certainly go to Amazon and buy the book. And I think that for next session, I hope that I have your company as well, which I very much appreciate. I know that this is a time when you are busy working, but I want to say thank you very much, and see you next time. So have a very nice day, and please keep connected. Any questions you may have, I will be happy to answer them in the following days. But for the time being, I release you to get back to your normal activities. Thank you very much, and have a wonderful day.